Climate change, deforestation, and other human-led catastrophes have ravaged our Earth. Due to environmental changes occurring unnaturally fast, the world and our ecosystems are unable to keep up. With animals struggling to adapt to these changes, it is essential for conservation research to devise a method to efficiently and effectively track wildlife activity to properly grasp the full extent of these shifts in biodiversity. As such, researchers from the San Diego Zoo have installed recording devices called audio moths throughout the Peruvian Amazon in order to more effectively monitor these changes, first in bird activity and other animals in the future. There are undoubtedly thousands of birds hidden within the terabytes of acoustic data, but amounting to well over 1,000 hours, it is impractical to manually sift through.
And that's why our team is using machine learning in order to better process this data. Unfortunately, the amount of label data that we have, which is essential for training our machine learning model, is quite limited, which is what led us to implementing data augmentation.
But what is data augmentation? Data augmentation is a strategy for working with smaller datasets. By making small modifications to our data points, we are able to simulate having more data than we actually do. Let's take a look at our augmentations as an example of this. Listen to this unaugmented bird call. We can add a pitch augmentation to it, speed it up, and even introduce noise. In this case, we're using Gaussian noise, but our pipeline also supports white and colored noise augmentations. Before we talk about the results of training on augmented data, let's first talk about our testing datasets. We tested on two datasets. First, we have our Xenocanto dataset, which is crowdsourced off the web. It is relatively clean with little noise. Our second dataset is our AudioMoth dataset. This is the audio collected from the Amazon. The bird calls are significantly less audible, but this dataset is more representative of field-collected data. Now we can move on to the results during testing after training our machine learning model on augmented data. To do this, we look at our receiver operating characteristic curves, or ROC curves, which help us determine how well our model can separate our classes. This is our ROC curve on our unaugmented Xenocanto data. But how do we read this? We have three lines here. A green line, which represents class 1, meaning bird positive, a black line, which represents bird absent or bird negative, and a dashed line assuming a random classifier, basically one that guesses. Our x-axis is our false positive rate, which is our false positives divided by our false positives plus our true negatives. It represents the bird negative data points classified as bird positive. Our y-axis is our true positive rate, calculated as our true positives divided by our true positives plus our false negatives. It represents the proportion of correctly classified bird positive data points. What's nice about ROC curves is that they can easily be compared using the area under the curve, the higher being the better at separating classes. Here we have an area of 0.95. After implementing data augmentation, we have an area of 0.98, a small improvement. However, this is on the cleaner Xenocanto dataset, which was already doing fairly well. What about our results on the data from the audio moths? We originally had an area of 0.65. Not so great. After training on the augmented data, however, we achieved an area of 0.77, a significant improvement. There's still work to be done and progress to be made, but we're one step closer to our goal of helping ecologists in their monitoring efforts.